Welcome everybody, good afternoon to you. My name is Leslie Smith. I work for a startup known as the U.S. Naval Research Laboratory in Washington, D.C. Unfortunately, Jerry, that I didn't get any stock options in it. But we just celebrated our first century anniversary, so I think it might make it. Anyway, so I'd like to start by setting expectations. I am not planning to give the best talk of the day. It's already been done. What I'd like to do is tell a story. Everybody likes stories, right? Everybody likes stories? So I want to tell a story about my curiosity in terms of how to best train deep neural networks, my enlightenment about learning rates along the way. And like every good story, my story starts once upon a time. I took my first baby steps, and I created something called cyclical learning rates that made it a little bit easier to train neural networks. And this story of mine, it has all kinds of wild adventures with faster and faster training of networks. And like any good story, we have heroes. And these heroes, they entered challenges. And against great odds, they won the challenges. And I will tell you about them. Unfortunately, my story does not end with they lived happily ever after. Turns out that enlightenment and curiosity is a never-ending story. The story still is continuing to this day. So I'm going to get started by, if you'll excuse me, talking about some of the basics of deep learning, which probably most of you already know, but it gives some context to what I'm going to talk about. So deep learning, which is a subfield of machine learning, we deal with neural networks, usually deep neural networks, which means they have many hidden layers, and each hidden layer contains trainable weights and biases where we act upon them by a nonlinear function. Now, I do have a laser pointer, and if I point here, nobody's going to see it. So you'll just have to follow along. I'm going to point to the first equation, and I do apologize. I do have a few equations. So we have an output from the previous layer that we have y of L minus 1, gets multiplied by this trainable weights, and biases are added. We act on it by a nonlinear function. And that gives us the output of the layer y of L. If you want to know what's happening in the neural network, you can do this recursively. You start with input, which we call x, and you act on it repeatedly, and then y subcapital L, that's the output of the network. This is a little bit easier to see pictorial. You have an input x, which in this case is a sign. Associated with a sign is a label. The label says that this input is a speed limit sign 20. It's not any of the other things. But if we take this input and we feed it through a network, something comes out that's not the same as the label. So we have a difference between it, which we call a loss, which is the difference of y sub L, capital L, and the label y. And we do some magic. I bet you didn't know I had magic in my talk. So we do some magic called backpropagation. So we change these trainable weights and biases so that the next time we were to send that same input through the network, what comes out is closer to the label that we want. Now you're all experts. If you weren't before, you probably already were, but now you're all experts in deep learning. That's all it's about. So what are learning rates? I mean, obviously, I'm talking about competition-winning learning rates. We have to know what learning rates are. Well, learning rates are the step sizes used in this backpropagation magic. If you pardon the next equation, we see that we have weights at time t, and if we want to know what the weights are at t plus 1, we're going to compute the gradient of the loss. The loss is the difference that I showed you on the previous slide. So I could show you again. See? That's the loss. So the difference, the gradient of the loss, in other words, the change of the loss, multiplied by epsilon, in this case, that's the learning rate. that tells you how to change the weights now, or how we change the weights now to get a new set of weights. That'll give us a better answer if we do it the next, we send the input through the next time. I'll make it easy for you. Okay, so long ago and far away, it had always been known that learning rates is like the most important hyperparameter to tune. If you make the hyperparameter, the learning rate, too large, the training will diverge, it won't work, you just get nowhere. And if it's too small, then the network will train slowly, but it also trains, and this is important, it trains to a suboptimal solution, so you don't get a very good answer, well, you get a suboptimal answer. So if you all remember Goldilocks, it has to be just right. So you have to get the learning rate just right. So how do you find an optimal learning rate? Well, the way it had historically been done is grid or random search, where you pick a bunch of points. You do a full training, you see how well, what performance you get out of it, and then you take the best one, and that's the learning rate, or the hyperparameter. It's the learning rate that you're going to use for your training. Well, I kind of thought this was time-consuming and, in general, inaccurate, because what if the optimal learning rate was in between some of the points you happen to pick? So I thought, well, is there a better way to do this? And I came up with this idea that I call cyclical learning rates. Am I making it hard for you to keep track of me? Just checking. So cyclical learning rates is you ever hear that close is only good enough in horseshoes? Well, close is also good enough with learning rate. So I thought, what if we only got close to the optimal learning rate? So let's take it, we get a reasonable kind of maximum minimum bound on the learning rate, and let the learning rate kind of go between, and hopefully it'll spend most of the time close to or at the optimal learning rate. So this idea actually proved quite sound. If you were close and you did this and you had cyclical learning rates that varied between the two, turns out in all my experiments that I would get an optimal solution out of it, as though I had run with the best learning rate. If I had gone through the effort of a grid search or whatever and found an optimal learning rate, then that would give me the same high performance answer. But something even better came out of this work, at least I think it is way better, and it called it the learning rate range test. And if you look at the picture at the bottom I guess it's your right, yes. My right too, actually. So it turns out if you do a training, you start training, and you start the learning rate at a small learning rate value. So let's say you don't know what the optimal is, or even what the bound should be, and you let it increase. What happens is the training will reach a peak, and that peak tells you what the maximum learning rate should be. And the optimal is going to be somewhat less than the max. So here's an easy way, and it's quick. You don't have to run to completion. You can do a quick run. So you can find what the optimal learning rate is in a much simpler and even more accurate way than running a grid search or a random search, or the typical way of doing it. So you said, oh, that's pretty cool. So I started doing this on everything. Every time I started running a new architecture, and et cetera, and I want a new data set, because training networks are very training data dependent. I'm sure you all know that. So I started doing this always. Well, time goes on, and we were happy for a while. But it turned out that there were new architectures like ResNets, and there was new algorithms like batch normalization. And when I ran ResNet with batch normalization, it didn't give a peak. So that's curious, or maybe I was curious. And I said, that's very strange. A lot of inventions come out of, that's weird. So I started going to larger and larger learning rates. If you look at the top right, you'll see that the learning rate actually in this test goes up to 3, which was, in my opinion, an order of magnitude larger than I'd ever seen been used for learning rates in the past. So I wondered what was going on. So I decided I would take just one cycle of learning rate. And you can see here, I go from a small value to a large value. And it turns out I got the red curve in this figure on the bottom right, which is different from a typical training. A typical training is the blue curve, where when you drop the learning rate by an order of magnitude, you get a jump. I assume most of you have seen that when you drop the learning rate, that the test or validation actually will jump. And that's why they say it's important to, it's important to get the learning rate right. But I got a different curve, so it goes up very quickly to mid accuracy, and then as the learning rate goes down, the accuracy shoots up. And I was able to get a very reasonable, actually a little bit better, but very quickly get an answer in about an order of magnitude less training time than was typically used for training such a network. Cool, huh? Anyway, more recent results showed that if the performance isn't good enough for that quick training, in other words, it depends on if you want fast or if you want more accurate. If you want more accurate, then you can actually add a tail that goes down, and you'll get a more accurate answer at the cost of a little extra training. So this was all cool stuff, but CFAR is really small and generally pretty quick. What about ImageNet? ImageNet's a big data set. Would these ideas work in ImageNet? So I tried it, and here are two different architectures. One is ResNet, and another is an Inception ResNet. And it turns out that doing this, using large learning rates, does still allow you to train very quickly. So that was cool. Now, it's always very gratifying as a scientist when other people pick up your work. I'm moving over here. When other people pick up your work and build on it and do amazing things. And it turned out that there was a group called Fastai, actually located here in San Francisco. I assume you've heard of San Francisco. They had picked up on these ideas in super-convergence, and they started entering some of the challenges, and they won. So the first one is Stanford had a DAWNBench challenge, and there was two parts to it. One was minimize the amount of training time it takes to reach an accuracy of 94% plus with CFAR10. And the other one is if you went on a cloud system to minimize the total cost of training, and again, reach 94% accuracy. Fast.ai won both parts of the challenge, number one. And Jeremy Howard, who runs the Fast.ai group, was interviewed, and he was gracious enough actually to mention super-convergent as one of the factors that was allowed him to be able to win this competition. Furthermore, one of his students, Radek, I'm not going to try to pronounce his last name, he entered Kaggle. Everybody here heard of Kaggle? Yeah? Okay, good. See, everybody's awake. That's nice. I like it when people are awake. So he entered, and he also was gracious enough to mention my paper on superconvergence. So here are some relevant publications. You can jot them down. They're good bedtime reading, because I'm sure they'll put you to sleep. Cyclical learning rates was from a few years ago, superconvergence, and then I also have been looking at different hyperparameters like batch size, momentum, and weight decay. So it turns out that the work that I did is equivalent to a batch of research that came out in the past year and a half. It's a large batch of research called large batch training, where you use a very large batch size. The difference, the only real difference, is I focused on the learning rate and the learning rate schedule, and these papers and these researchers have focused on the size of the batch and being able to use large batch sizes. And the work that I've done here, I mostly used medium-sized batches, but it turns out that all this work is very related. So now, I still have 8 minutes, but this seems like a good place to ride off into the sunset or happily ever after. But I'm not done yet. So enlightenment, curiosity, learning, all this is a never-ending story. This is still going on. More recently, and you should be honored, this is the first time I'm presenting this recent work in public. You honored? Yeah, okay. So the question I'm asking is weight decay more important than learning rate? Why am I asking that? So let me explain. First of all, what is weight decay? Weight decay is very closely related to what is known as L2 normalization. The first equation, I'm sorry, I have another equation. The first equation, you notice that the loss is equal to what I said before, the output from the network minus the label. So we're trying to make sure that it matches the label, but we add a new term, which is 1/2 lambda. Lambda in this case is what I'll call the weight decay coefficient times the square of the norm of the weights. So that changes the way we're going to update the weights. And the third equation, where I rearrange the terms, you see we now are taking the weight at the previous time, and we're decreasing it by an amount that's epsilon times lambda, where epsilon is the learning rate, and lambda is the weight decay coefficient. So we're decreasing it by what I'm going to call an effective weight decay. Okay? Is that clear? Everybody got it? Any questions? Oh, I'm not supposed to ask any questions. Well, actually, I will, but we'll get there. So anyway, the question that I asked myself is, we now have two terms that contain the learning rate. When we change the learning rate, because we have a learning rate schedule, which term is more important in terms of the training? I could ask you, do you have any ideas? Is it the first term, the weight decay, the effective weight decay? Or is it the second term, the gradient, that it makes important the learning rate schedule? So I decided I would do an interesting little quick experiment. You see on the bottom right, the blue curve is the normal way of training neural networks. We're at 150 epochs, we drop the learning rate by an order of magnitude, and then at 225, we drop it again by an order of magnitude, and we get a good training out. So I said, well, what if I set weight decay to 0? You know, what's going to go on? Well, you see the magic jump when how the validation accuracy jumps when we drop the learning rate? You could say yes. Yeah. It's clear, to me at least, I hope it's clear to you, that that drop is due to the first term, the weight decay, and not what people generally assume, that it's due to the fact that the gradient, we're multiplying the learning rate by the gradient. Because when we just have that gradient term in there, we have a very small kind of bump, really. It's not even a jump, which is different than what most, well, shall we say, conventional thinking in the deep learning community. So I decided to take this further. So on the left-hand side, top left-hand side, what I did here is two things. First one, the blue curve, I have a constant weight decay, and I let the learning rate drop by orders of magnitude at 2 places. And we get a small bump at 150 and 225. The other thing I tried is I kept learning rate constant and dropped weight decay, and I got the red curve or orange curve, whatever it is. You can see, which is a little surprising, that decreasing the weight decay has a much greater effect in terms of that jump in accuracy than the dropping of the learning rate. So it's really the weight decay that's making a difference. This implies to me that weight decay has been hiding behind learning rate. And we've all been tuning the learning rate schedule and mostly affecting the weight decay schedule, without realizing it, and maybe they need to be two separate schedules. So, me being me, I went ahead and I said, well, can I figure out what the maximum weight decay would be? I did the same thing as the learning rate range test. I did a weight decay range test, and sure enough, as you go along training and as it goes along and weight decay is increasing, there is a peak. So you can figure out what the max weight decay should be, and from that, the optimal weight decay is somewhat smaller. And I also started saying, well, what if I have a separate schedule for weight decay than for the learning rate? And I started looking, and it looks like having a large weight decay that you can figure out from the range test early and letting it decay independently of the learning rate actually is useful when training is difficult. So in this slide, I'm focusing on when training is difficult with, first on the left-hand side is a large batch training. There's something known as a generalization gap in large batch training, where if you use large batches of data, the final accuracy is generally lower than if you trained with small batches, but it takes longer to train. So it turns out by controlling weight decay independently of learning rate, that one can close that gap significantly. You can see the blue curve is with a constant weight decay, and then the red curve is with a decaying weight decay, and the final accuracy is 0.5% better, which is a start, at least in terms of closing the gap. And also, if you try and train fast, shorter and shorter, fewer epochs, the gap actually increases. And then decaying weight decay seems to be even more useful. All right, I also want to point out something that is, I don't think generally known, is the hyperparameter relationship, which I think is very valuable. And it relates the fact that learning rate, weight decay, the total batch size, and momentum is kind of constant. So if you have an idea of what those variables are, and you say, well, I want to change some of them, and be able to figure out if changing some of them and using a different set can give me a better final answer, you can use this as a rule of thumb, which is a useful, it's a very practical rule of thumb that you can use for being able to change and test different values of the hyperparameters. So, in conclusion, enlightenment, I think the main thing, the moral of this story is, curiosity, enlightenment, continual learning, lifelong learning, whatever, it's important to all of you. You should all keep on learning always. I am a highly unconventional, curious person, and if anyone wants to collaborate with me, send me an email. But I think that's the moral of the whole story, is be curious. Be curious all your life. Always try and learn new things. And for novel things, I think that the fact that weight decay has been hiding behind learning rate schedule is important. And that from a practical perspective, for those practitioners who are actually training neural networks, having an equation that you can use to get these hyperparameters in an optimal way is useful. So if I had time, I would actually take questions, because being an unconventional thinker, I don't let convention stand in the way. But no pressure, but if you have a highly insightful question where the whole room will benefit from them, raise your hand. Okay, you.
Does your work apply to RNN?
I have not done work with RNNs. My intuition is it would, but the truth is it's all in the experiments. You have to do the experiments to know. I can make up stuff I do actually. If you look at all the times I'm wrong versus the times I'm right, the wrong, anyway. I thank you for your time and attention.